Okay. Good morning, all of you. Welcome to the online classes, TRA Society. For so many days, we have discussing about ray optics. In that, some points we have already discussed. That is, when the light ray is moving, entering into one medium to another medium, what are the properties they are going? Let us. We have already discussed. Once you take a recap of those we have already discussed. One, whenever light ray is passed from one medium to another medium, there are two possibilities that takes place. One is a reflection, another one is a refraction. While refraction is considered, there are two laws we have discussed, and whenever refraction takes place, the three rays, what is incident and refracted and also normal line, these three are in the same plane. And second one, the angle of incidence and relation between angle of incidence and angle of refraction we have discussed. We are discussing those laws, and mirror equations also we have finished. Now in the last class, what we have discussed, that is critical angle. We are discussing about total internal reflection. What is critical angle? We have already finished. When a ray of light is passed from denser medium to rarer medium, the angle of incidence in the denser medium is known as, that is, critical angle, at which the refracted angle becomes 90 degrees in the rarer medium, that we have discussed. So in that case, the refractive index of the rarer denser medium, that is given by 1 by sin c, that we have discussed. Now, what is total internal reflection? Actually, before going to see total internal reflection, we should know what is critical angle. That's why we have discussed about that. Now, what is total internal reflection? This is also one type of reflection. Reflection means the light ray has entered from same medium from which it is coming, and again it returns to the same whenever it is possible. This is when a light ray is passing from denser to rarer medium. That is most important point here. Whenever light ray passes from denser to rarer, then if the angle of incidence, which is greater than its critical angle, we have already discussed what is critical angle. If it is more than that critical angle, what happens? Then the refracted ray enters into the same medium. So you can see incident ray and refracted ray, both these two are in the same medium, that is in denser medium. This is whenever light ray entering the same medium, what we call it is a reflection. Therefore, this is also total internal reflection that we have seen in this one. So here three colors of light rays are observed here. One is green light, the green light ray, which shows just that is a refraction of light. A certain angle, it is theta 1 and theta 2 is a refracted ray. And red ray, you can see, passes through this interface between rarer and denser medium. Then what is refracted angle now? It is exactly 90 degrees in the rarer medium. So here the red colored angle inside the denser medium, that is critical angle. That's why it is represented as theta c. C indicate critical angle. Now third blue color ray, you can see it is started from glass, and again blue ray you can see in the same glass medium, means denser medium to denser medium, both these two. So this is related to what our topic, total internal reflection. So whenever light ray is passing from denser to rarer medium, if the angle of incidence is greater than this theta c in the figure, you can see greater than critical angle, then the refracted ray again enters into the same denser medium. So this phenomena is called total internal reflection. Many ask what is the use of this total internal reflection, why we are discussing. So there are number of uses are there, number of applications are there. Naturally, this total internal reflection, we have some phenomena you can observe. By using this, how we can use this phenomena in our daily life. Those are some applications of only some I will discuss. Let us say, first one is optical fiber. We are heard about this one. Nowadays, we are using cell phones and all these, how the signals are coming from one place to other place. Are you using any wires? No. Without wires and all these, cables are there, some here and there, some towers, cable towers you can see. So these optical fibers are inside the ground. How you can transmit these all? Here in this optical fiber, what is going on? These are used for transmitting audio and video signals. You are hearing my lesson. You are far away from me, but you can hear without any interaction, direct medium here. What is the medium here? Optical fiber is there. So here, these are used for transmitting audio and also video signals through long distance. Longer distances we can send in different ways. One of those ways, nowadays we are using these optical fibers. A signal in the form of light. Here, the signals are sent through light rays. You can see red light in this pipe. This is optical fiber. Optical fiber means, you know what is it? Thin, very thin fiber, glass made up of glass, a very small thin one. From this enters this, but here it takes place total internal reflection inside. It has to enter more than its critical angle. So what happens? It does not come out. Again enter into the same glass. The blue colored one is small. There is core and cladding is also there without dispersing in that way and that way. All the rays has entered into the same pipe. It seems to be very big. But the thickness of this is just our hair. How much small it is, you can understand. In that small region, whatever the ray is entered, it takes place total internal reflection and again enter into the same here. Number of times it takes total internal reflections and comes out. So whenever the quality of audio and video at the beginning, at the entering stage, the incident ray, the same quality is maintained at the other end of this fiber also. So the quality does not change from the beginning to the end. That is main thing. These are optical fibers. So in examinations, we should not go details about what are the applications of total internal reflection. That is the only question. So you can remember the side headings and you can write simply what is going on inside related to our topic now only we are discussing. Therefore, as far as this optical fiber is observed, here we can say light ray takes place in total and internal reflection. The signal is in the form of light ray. It takes place total internal reflection inside the optical fiber. This is the application. One of the applications of this total internal reflection. And in general, in nature also, brilliance of diamond, you know, the cost of diamond is more than gold. Why? What is happening here? It is due to its shining. This is one type of a stone, natural stone. But you can see here there are number of surfaces. While the surfaces are increasing, the cost of the diamond is also increases. Actually, what is the principle involved here? Generally, the light ray has entered from air to this diamond, which is whatever it is. The both of these two media, glass and diamond, the air interface, the critical angle is very, very small, 24.4 degrees. Generally, the light rays enters more than this critical angle. All the light rays fall on this diamond more than this critical angle. Then what happens? They enter into the diamond again. While they are entering into, again, that takes place in number of times refractions and comes out. So number of times refracting means its intensity increases. Number of light rays comes out. From one light ray is entered, you can see number of light rays from different surfaces. There are more surfaces on them. By cutting the diamond suitably, multiple total internal reflections can be made. Means number of surfaces has to be cut so that from each surface you can see light ray. You are sending only one white ray, that comes out in different surfaces. So it seems to be brilliance. It shines. So brilliance of diamond is one of the another application of total internal reflection. And third one is in deserts, you can see this type of mirages. What are mirages? This is actually we cannot see any water far away distance in the deserts, but it seems to be a water. This is only optical illusion. We call it as optical illusion. But while you are going to that water, there is no water. Why it is becoming like that? In deserts, the surface is very hot. It is desert means completely sand with high temperature. Very hot sand exists. So whenever very hot on the surface, what happens? That density, whenever very hot, density is less. Therefore, the atmospheric surface we can divide into two. Where is nearer to the sand, we call it as very hot surface. That seems to be lesser density area, lesser density region. And going up, comparatively this, the temperature is less. At the top layer of the sand or the upper layer of the sand, you compare these two. You can see in this diagram, blue colored one and white colored. White colored one is lesser density. And here we are writing cold air, means you don't feel it is very cool. In deserts, no cool it is. But comparatively, when seeing the nearer the sand and above the sand surface, it is cool. The temperature is less. Therefore, this colder one seems to be denser media, and nearer to the sand is, which we call it as less denser media. So light, a tree is there. So light has to come from the tree. How you can see this tree? While the light rays has come from one place to again coming to the hot air, what happens? Means first light rays entering into the hot air means it is entering into lesser and hot air, cold to hot. What does it mean? Denser to rarer. The light rays are entering from denser to rarer. What happens? The light rays does not enter into the next medium, which is hot air. You can see it is curved one. The arrow mark shows again these enter into the cold air. That is denser region. Whenever light is entering from started from denser medium and refracted towards same denser medium, then how you can see? While you are standing far away from this tree in the deserts, you can see tree reflected from another one. The bottom of the tree, you can see the tree image. While whenever you can see two opposite images, one is upward, the image is inverted again downwards. It seems to be water is there, no possibility to see two images. So while observing this illusion, this person feels that there is water. So this is, and the same you can see in the hot summer on cement roads or tar roads. You can see in hot summer there is a water is flowing on it, but actually there is no water. Did you observe in summer? This is due to light rays coming from denser to rarer medium, again enters into the same denser medium. This phenomena, these are general examples of total internal reflection. And now these are, so you can remember optical fibers, brilliance of diamond, and mirages. Just you remember these points. You can explain your own words, that gives you full marks. So generally the question related to what is total internal reflection, what are its applications, that's all. Now coming to another important one, refraction through a prism. You know what is prism? Prism consists of five surfaces. Triangular shaped. Here in this diagram we are showing ABC is a prism. Actually Three-dimensional, if you are observing, there are two surfaces, rectangular surfaces are attached each other. Those are AB and AC. Those are rectangular ones. Those two are attached. Then you can see a triangular shape. Here is also ABC is one surface, and opposite to ABC another surface is there. In only we are writing two dimensions. Generally, whenever there is a prism, we are showing only ABC like this, a triangle. But you don't feel this is a triangle. This is three-dimensional one. So this prism consists of two surfaces. I told you two rectangular surfaces and bottom is one rectangular one. When two rectangular ones are fixed each other, you can see at the bottom BC is also rectangular one. So three rectangular surfaces and two triangles. ABC is a triangle, opposite to that other side, a triangle is there. Therefore, there are five surfaces to any prism. So among all these five, two surfaces we have to consider. Those are most important here as we are consider this refraction. Those are these two surfaces. One surface is called incident surface and second surface is called refracted surface. So AB, incident surface, means on which the light ray has to fall, that is incident surface. AC is the surface from which the light ray comes out. So here, let us consider in this diagram, see carefully, and it is better to note down the diagram while this is a derivation we are going to see how to find out the material of this prism refractive index. The derivation is determination of how to find out the material of the refractive index of this prism. The prism is made up of certain glass. So what is the refractive index of that glass made up of this prism? So while taking derivation, we will take some equations. This is very simple, but the same diagram, once you observe carefully, you explain the diagram carefully. What are those things? ABC is a prism, AB is the refracted surface, and AB is the incident surface, and AC is the refracted surface. And here PQ is the incident ray, while PQ is entering into the prism. QR is the refracted ray inside the prism, QR. And RS comes out, emergent ray, we call it as emergent ray. PQ is incident ray, QR is refracted ray, RS is emergent ray, comes out. This is one light ray is taken and total derivation will take place based on this one light ray. So here there are different angles also we have to consider. One is angle of incidence at AB. Whenever you find out incident or refracted angles, what you have to do? At the point of incident, we have to draw a normal. The dotted lines meet at N. A normal is drawn to AB to meet at QN. Dotted line QN is a normal drawn at the point of incident Q. And similarly, NR is also another normal drawn at emergent ray point at R, from which point it comes out. So these two normals meet at N. So in this, with this angle, what is the angle made by PQ? That is incident ray. That is angle of incidence. So angle of incidence at AB, this is taken as I. Now QR is a refracted ray. While there are two normals at Q and R, you can see two refracted angles inside the prism. R1 and R2 is considered, where R1 is equal to angle of refraction at AB, R2 is angle of refraction at AC. Now again, finally you can see the emergent ray RS makes an angle with the normal, that is called angle of emergence. It is taken as small e. That is, so incident and emergent angles, both these two are in air. Two refracted angles inside the prism, you should remember. And not only these four angles, fifth angle we are taking as delta, which is the angle of deviation. Angle of deviation, you see, in this figure angle RM and some number you can write outside at M you can see. This is exterior angle of incident and emergent angles. What is angle of deviation? Generally, you will ask the question. The exterior angle of incident and refracted rays is called angle of deviation. Okay, not inside the angle, not angle PMS. Remember, PM is the incident ray, MS is the refracted ray. While you are producing RS, you can get incident ray. You are producing PQ, you can get PQM, that is the incident ray. So the angle between these two means that is outside, not interior. So you should remember that one. So now let us start the derivation. What is it? First you have to take AQNR is a quadrilateral. In this quadrilateral, opposite angles, angle AQN, you know what is angle Q? That is exactly 90 degrees. And similarly, why? Because at Q you are taking QN is the normal. Similarly, NR is also normal. Therefore, angle AQN plus angle ARN, 90 plus 90. So the total angles, that is 180 degrees. Now, opposite to this quadrilateral, angle QAR, which we can take angle A, which we call it as angle of the prism, angle A plus angle QNR, opposite to that is also 180. Why? Because the sum of the four angles in any quadrilateral is 360 degrees. Angle Q, angle R is 180. Therefore, remaining 180 is angle A plus angle N. Simply we are taking. So we are interested not to take angle AQN plus NRQ. That is not in interest now. Our aim is to find out angle of prism. Therefore, angle A plus angle QNR, angle QAR plus angle QNR is equal to 180, equation 1. Now, you take in triangle QNR, a small triangle, inverted triangle, you can observe opposite to QMR, you can see another triangle with the normals on this refracted ray in this QNR. The sum of the three angles is 180 degrees in any triangle. Therefore, you are using that theorem R1 plus R2, both refracted angles plus angle QNR. QNR is this total. All these three angles is 180. This is equation 2. So equation 1 and equation 2, both these two RHS side 180. Therefore, you can equate LHS sides. So 2 equation is equated to first equation. Therefore, R1 plus R2 plus angle QNR is equal to A plus angle QNR. Okay. And here QNR cancel out. So we can get another equation. R1 plus R2, both refracted angles sum is equal to angle of the prism. So this derivation is very, very important. While derivation is directly given for essay type questions, then you have to derive this equation. And also problems may be given based on these equations. The refracted angle is so and so for the equilateral quartz prism. We may ask like that. Equilateral quartz prism means angle A is 60 degrees. So A is given, refracted angle 1 may be given. What is the other refracted angle? Like that questions may be asked. So equations also very important. So for here now equating quadrilateral, using quadrilateral properties, we are taking 180, A plus N is equal to 180. And another in the triangle property, sum of the three angles is 180. We are writing angle R1 plus angle R2 plus angle N is 180. So equating these two, we can get R1 plus R2 is equal to A. Now, the total deviation you see in your figure, delta value, that is, we have already discussed, it is exterior angle. So when two lines in any triangle, exterior angle is always equal to the sum of opposite interior angles. Okay, by using that, the exterior angle is sum of opposite interior angle. Therefore, delta opposite angle is I minus R1, left side angle. You can see I minus R1 in the above triangle. Okay, plus this side triangle, what is the angle inside? Emergent angle is E. Inside that means E minus R2. You carefully observe how these angles are I minus R1, E minus R2. Can you understand? So from this, while combining these two, I minus I plus E minus you can take out common, R1 plus R2 you can write. Therefore, delta is I plus E R1 plus R2. By using the above third equation, you can write A. So deviation angle is equal to incident angle and emergent angle. We have to add these two and subtract angle of the prism. That is equation 4. So like this, you have to derive 4 equations. Now this delta remains the same if I and E are interchanged. The important thing is how these two are related. We are discussing here incident angle and emergent angle are both changed. What happens? In that case, delta should be same. Physically, this is related to the fact the ray can be traced back. Both these two are equal. What does it mean? While you are changing, this is incident angle, this is refractive. Or you take this is emergent angle. If you are changing, this is incident, emergent as considered as incident, that incident changes as emergent. Like that, you can alternatively you can change it in that case. So when it is possible, the deviation angle is minimum. It can be possible. Both these two may be interchanged in only at single case. That single case is when the angle of deviation is considered to be minimum. At this condition, actually what is happening? In the minimum deviation condition, the light ray, we have discussed already, total internal reflection is a phenomena at which the angle of incidence is more than critical angle. Similarly, here also at a certain angle, at a certain incident angle, we can see this minimum deviation. In that case, what happens? The refracted ray inside the prism exactly parallel to the base of the prism BC. ABC we have taken, that is the prism. BC is the base. Exactly, refracted ray, where is the refracted ray? Inside the prism. So inside the prism, it is exactly parallel to the base of the prism. In that condition, exactly you can tell the deviation angle if you are calculating, that is minimum value you can get. Can you understand? That is called minimum deviation. So it is represented to tell capital DM may be given in the textbook. For our convenience here, I have taken red D, red letter D, indicate minimum deviation. In that case, two conditions are possible. Whenever it is parallel to base, the refracted ray parallel to base inside the prism, the I is equal to E. First condition is incident and emergent angle should be equal. And second condition is, as it is a just parallel to base, both refracted angles R1 and R2 should be also equal. R1 is equal to R2 and I is equal to E. No question about this. So the angle of deviation depends on angle of incidence. Okay, this is the condition what is happening. How we can observe? Is it possible light rays are falling on a prism at different angles, and even though you are taking experimentally, can you identify the minimum deviation? Is it possible? For this, we have to do in practical, we are having an experiment to determine angle of incident and angle of deviation. Different incident angles, we can get different deviation angles, not minimum deviation. You remember, deviation angles you can get easily, you can find out. So we can draw a graph between incident angle for 30 degrees, what is the deviation angle? For 40 degrees, what is the deviation? For 50 degrees, what is the deviation? Like this, by different values of I, different values of D values, that is delta values, you can find out. a plot between this delta value, that is deviation and incident, we can get a graph. So the minimum deviation, theoretically, we are explaining here, whenever the light ray, the refracted ray is exactly parallel inside the prism, is not possible to see with our naked eye. We cannot see it. But you can see incident ray and refracted ray by taking images. You can take a pins or some other things. You take incident ray, this is a refracted ray. By producing incident refracted rays, you can get deviation angle. But you cannot find minimum deviation. That is a problem. That's why to find out this minimum deviation, graphically, we can trace out that. How it is taken. You draw a graph between I and D. This is called ID curve. Can you see this graph? The graph is taken angle of incident on x-axis and angle of deviation on y-axis. Deviation angle. For different angles, you can get, finally you can get this curve. From this curve, usually you find out I1 and I2. For example, you have taken I1 is a incident. What is I2? I2 is here emergent angle. I1 and I2. Related to this I1 and I2, you can see delta. So from this graph, what is the minimum value? The least curve where it is minimum. In this curve, you find out minimum delta M. Here you shown in this diagram, we have taken the delta M as capital D. So at D, what happens? I1 is equal to I2 in this diagram. What I have already discussed, I is equal to E. In place of I2, we have taken E, whatever it may be. I1 is equal to E means incident angle and emergent angle should be equal. So whenever these two are equal, one perpendicular line you have drawn here, and from this you can find out capital D. Is it clearly? Can you observe? This is most important. So at D point, what are the angle of the prism? Angle of the prism we have already taken third equation. R1 plus R2 is equal to A. From that, what is R1, what is R2? Whenever I1 is equal to I2, the refracted ray is parallel to base, R1 is equal to R2. Both these two are equal. Therefore, I have taken A is equal to R plus R. Both are taken. R1 is equal to R2 is equal to R is considered. Therefore, R plus R means 2R. So from this, what is the refracted angle? R is equal to A by 2. This is equation number 5. And now, what about incident angles? I1 is equal to I2. From this graph also we can identify. So from I1 is equal to I2, what is I? I is equal to, first you take the equation, D equation already we have taken, I1 plus I2 minus I1 plus E we have taken. In the fourth equation, I1 plus E minus A. So I1 means I plus I, E is also considered as I, both are equal, I plus I minus A, that is 2I minus A. Therefore, from this, what is I? A plus D by 2. Okay, this is equation number 5. 5 and 6, this is. So, from 5 and 6 equation, R we have taken as A by 2, I is taken A plus D by 2. You remember this D is minimum deviation, not deviation. Okay, minimum deviation. That minimum deviation plus A, you have to add up these two divided by 2, not D by 2. A plus D by 2 you have to do. Okay, now what is the refractive index of the prism? We have taken as N21, or refractive index is generally represented by mu, which is equal to sin I by sin R. Incident and refracted angles we have taken as like this. So in place of sin I am substituting sin of A plus D by 2 by sin R. Sin R means A by 2. Therefore, refractive index of prism, material of the prism, that is, prism means material of the prism, is equal to sin A plus D by 2 by sin A by 2. While writing, the students, they committed mistakes without any brackets. If you are write a plus d by 2, it is quite wrong. Why? Because it becomes a plus d by 2. Therefore, be careful. A plus d should be in brackets. Means first you have to add up a and d, then only the sum is divided by 2, not d by 2 or a by 2. So a plus d by 2 by. Similarly, this is sin a by 2. Some are writing sin a by 2. That is also wrong. Only you have to divide sin of angle may be divided. Only a by 2. So be careful while writing this equation. Sin a plus d within bracket by 2 by sin a by 2. So this is derivation for refractive index of the prism. The angles A, you can measure, you take any prism and draw this face, triangular face, that you can get ABC. By using your protractor, you can measure what is the angle of the prism. Generally, it is 60 degrees. For while you are conducting an experiment, these are equilateral glass prisms are given to you. This is very important as far as theory is concerned, and also as a practical point of view also, this may be given for you. Find out the refractive index of the given prism. You are given a prism and you find out the refractive index. Okay. Now a short question maybe is there. If it is very small prism, sometimes the angle of the prism is very small. For a small angled prism, then A is very small, means what about D? D is also very small. Then how to write the refractive index? The above equation which we have derived a plus d by 2 by sin a by 2 is just changed, as there is no need to take a plus d by 2 and a by 2. You have to, there is no need to divide by 2. Another thing is there is no need to take sine values. If theta is very small, sine theta is taken as theta. We are having approximations. Sometimes while taking derivations in mirror equations also, we have observed this type of tan theta is equal to theta, sine 2 theta is equal to only 2 theta we have taken. If the angles are very small, instead of that sine, tan, those values, instead of that, only the angle you can take. So removing sine and by 2 also, what is the refractive index? A plus D only remains in the numerator and only A remains in the denominator. Therefore, refractive index is equal to A plus D by A. So from this, sometimes you have to find out what is a minimum deviation in a small angled prism. Means that value is A into refractive index minus 1. While you are simplifying the equation A plus D by A, you can write A by A is 1 plus D by A separately you can write. So, and from this A, you can find out as a refractive index minus 1. A into refractive index minus 1 is also D. This is also a remembrance, the importance point. While it is small angled prism, the angle of deviation is 4 degrees. Refractive angle, refractive index may be given. What is the find the deviation? Or sometimes the deviation angle is so and so. Find out refractive index of the prism. While you are seeing refractive index, immediately some going to the same formula sin a plus d by 2 by sin a by 2 formula, but that is wrong. Therefore, you should be very careful. In case of very small angle, just equation. Okay, and a plus d by a. That ends the lesson. So you remember this. Thank you very much. Tomorrow we can see some other derivations and remaining part of this ray optics. Tomorrow we can end the chapter. Thank you all. Thank you, all of you.